Welcome back. Now we'll look at paper 13 from May-June 2023. And as always, since the mark scheme is available, then as well as watching this video, I will also recommend checking the mark scheme. And of course, if the video is too slow, then you can watch at 1.25 or 1.5 times the speed. Okay, so yeah, first it's a little strange, right? We're starting with a logic expression. Right, so yeah, okay, here then, we just want to write the logic expression for this truth table. Now, to be honest, I mean, one way you can do it is something called the sum of products. And, you know, sometimes they do that. And I guess, well, the way you do that is you just look. You look at where the, okay, let's say where the outputs are 1. So, of course, right here. And yeah, obviously, well, this one and this one. And then basically, well, we just look at the inputs. So here, well, the inputs A, B, and C, right, they're all 0. So, well, okay, therefore, right, that's going to be not A. Right, then we go and not B. Right, and then we go and not C like this. Alright, then if we look at the next row, so the next row, well, A is 0, B is 0, so that's well not A and not B, right, then C is 1. So in this case, well, that's going to be not A, right, yeah, and not B, right, and C. And in this case, right, we would just all them together again, and yeah, of course, likewise this one, that's going to be what A, right, and not B, right, yeah, and not C. And of course, right, that's going to be A, right, and not B, and C. Now, I mean, this is how you would usually do it. But this one they actually simplify, which is yeah, a little strange because, well, usually they sort of tell you not to simplify. And I suppose here, I mean, if you just look at this, well, if we look at yeah, all the cases where x is 1, well, maybe we can just notice, right, that you know, obviously b is 0 in each case, right? So in this case, we can actually just simplify this, well, just to not b. Yeah, so I think that's right. That's fine if we just write it like that. Okay, then we want to complete the truth table for this logic circuit. Okay, so let's just write the logic expression then. So this one, well, that's going to be A and B. And yeah, I'm just going to write down the kind of words. Right, okay, then here, well, that's going to be not C. And this one, well, of course, right, this is just the whole thing. So let's say, well, yeah, obviously this. And then, yeah, kind of XOR this. So here, and to be honest, right, I'm just going to use the short notation. So, of course, the dot means and. Right, the plus, this means or. And then, yeah, the bar, right, that's going to mean not. So I guess, yeah, for example, not C. Right, so this one here, we're A and B. So, of course, well, let's just look for where they're both 1. So in this case, right, they're both 1. Here, they're both 1. Right, then everything else is going to be 0. Right, then the next one, okay, we want to go not C. So, right, let's just go not C like this. And, of course, this is just going to invert. So 0 becomes 1, 1 becomes 0. So, yeah, just 1, 0, 1, 0, 1, 0. Okay, just like that. Then we want to XOR them together. So, right, yeah, I suppose here we don't really need to write that because, of course, well, that's just going to be X. Right, so, of course, XOR, well, when they're different, it's going to be 1. So, right, okay, 0 and 1, they're different. Okay, therefore, it's going to become 1. Right, here, they're the same, so it's a 0. Right, different, yeah, same. Different, same. Right, same and different. Yeah, is that correct? Yeah, okay. And of course, you know, with these, I think it's good to double check, right? It doesn't take too long. Right, a university has 2 sites. Each site has several computer rooms. The computers are all connected as a WAN or wide area network. Identify 2 differences between a WAN and a LAN, right? And of course, right, LAN, local area network. So let's say, right, WAN. Yeah, maybe, or let's say A, right? So yeah, a WAN. Is a network spread across a large geographical area, right? E.g., you know, different cities or different countries. Yeah, or let's say it is a network. Right, okay, yeah, let's say spread, right, over a large, I guess what you say, large physical area, or yeah, geographical area. Or let's say, yeah, e.g., I don't know, maybe different cities, right, slash countries. Right, yeah, different cities slash countries. Right, let's say, yeah, well, in contrast. Right, let's say what a LAN is, well, yeah, I guess a LAN is, you know, 1 room or 1 building. Yeah, okay, right, let's say that. Yeah, a LAN, right, is a network. Or let's say, yeah, in 1 room, right, slash building. Right, and then I mean, well, let's think about the next one. We can say probably we can mention what a LAN is going to be faster, right, or a LAN is going to have lower latency. So yeah, I think I might say that. I guess let's say right, due to close proximity, or yeah, closer proximity of devices. Yeah, I guess, well, let's say to each other. Or yeah, let's say the LAN. Yeah, okay. I mean, probably it's going to be faster. Like, it's definitely going to have a lower latency. Yeah. All right. Let's say, yeah. Okay. All right. Okay. So let's say we'll have a lower latency. Right. And let's say, yeah, and probably a higher data transfer rate. Right. Yeah. Data transfer rate. I mean, that's not necessarily going to be true because, well, maybe you say, for your LAN, you've just got some, cheap switch or cheap router. Whereas maybe, for your WAN, you've got some, super expensive, super, yeah, obviously, and, just, well, sort of, yes, let's say super powerful, super efficient hardware. Because, well, obviously, for a LAN, right, maybe it's some like multi-billion-dollar company that's got this WAN, right? Therefore, of course, they're going to have a fast network. Whereas, yeah, LAN, maybe, yeah, of course, you've got some, cheap second-hand router. So, yeah, I mean, obviously, a LAN is not necessarily going to have a higher data transfer rate. But, I mean, you can say, well, it's going to have I mean, like, yeah, I mean, okay, most likely it's going to have a lower latency. And of course, like, the difference between, well, latency and transfer rate. Latency is going to be the speed. Okay, let's say, well, this is, our computer A, right? This is, yeah, computer B. Well, latency is just how long it takes, right, for A to send to B, right, and then, B to send back. Now, if this is in the same network, I mean, this will be, let's say like 1 millisecond, because of course, this is going at the speed of light. Now, if of course I don't know, yeah, okay, maybe you're in a different country, well, in that case, right, obviously, if A is sending to B, it's going to be a long distance, right? Therefore, yeah, maybe, I don't know, this one takes 100 milliseconds, this one takes 100 milliseconds coming back. Right, therefore, maybe this one has a latency of 200 milliseconds. But of course, we could say that again, like I don't know, let's say because maybe the hardware here is better, right? This might actually have a higher data transfer rate, although the latency is actually worse. Right. Anyway, the network uses different topologies in different areas of the sites. In one building, there are 5 computers connected in a mesh topology. Describe what is meant by a mesh topology. Right, so a mesh topology, well, I mean, let's just draw a sort of quick diagram. Right, I mean, let's just do it with 4. Now, of course, you can have a full mesh where we say, well, in a full mesh, then every device is connected to every other device, and they're going to be connected in a point-to-point connection. Of course, you could also have a partial mesh, because, I mean, the problem with full mesh is that, well, here, what if we have 4 devices? Is that going to be, yeah, I think, right, that's going to be 6 connections. Now, if we have 5 devices, I think then it's maybe going to go to 10 connections, possibly. 10 or 11. So the thing is, the number of connections we need, right? Or I mean, okay, basically, let's say the amount of wiring, right? The amount of wiring that we need is just going to grow super fast. Like if we have, let's say, 20 devices, right? Then we're going to need like hundreds or possibly even thousands of wires. I think actually just hundreds. And to be honest, you can actually calculate the formula for, let's say, the number of connections you would need, right, depending on the number of nodes. And it's actually not too difficult to calculate the formula. Like if you just think, well, okay, let's say you have, one, well, let's say if you have 1 device, I guess you need, right, no connections, right? If you have 2 devices, well, then you need 1 connection between them, right? If you have 3 devices, well, I mean, let's think about that, right? 3 devices like this, of course, right? You got what, 1, 2, 3. Right, if you've got 4 devices, I think we said, well, that's 6. So if you notice here, well, okay, this one just plus 1, right? This one plus is 2, this one plus is 3. Yeah, therefore, if you have 5 devices, it's going to plus 4, right? It's going to go to 10. So I mean, hopefully you can see, right, that's going to grow quite quickly. Right, anyway, of course, right, so this is going to be a full mesh, but we can also then have a partial mesh, because maybe we say, I don't know, maybe this is computer A, right? Say this one's quite important. Maybe this is some sort of server. And maybe this is like a printer or something, and then this is just some random device where it's not that important. So we might want to have, let's say, everything can be directly connected to the server, but for example, let's say A connected to sort of, I don't know, well, let's say B. Let's say A connected to B is not important. you know, since they don't sort of communicate that much. And of course, if they do want to communicate, well, then A can send via this device, you know, which is then going to forward it onto this one. So yeah, I mean, the sort of packets can also be routed, yeah, around the network like this, right, via an intermediate device. So let's try and explain that. We can say, yeah, maybe, okay, I mean, obviously, right, let's say in a full mesh, right, yeah, in a full mesh network. Right, let's say, yeah, each device, or you know, each node, each device, right, is connected to all others. And we can say, well, yeah, with a dedicated wire. Right, let's say, yeah, I mean, well, we can say, right, let's say, maybe dedicated point-to-point, yeah, like point-to-point connection or point-to-point wire. Yeah, I mean, let's say wire, I think that's fine. Yeah, and of course, you know, the advantages, I think we don't really need to mention that. Yeah, I think this one they do mention in the mark scheme though. So they do say that if, let's say, if one of the wires breaks, then of course, I know, okay, let's say this wire here breaks, right, then of course, yeah, we can just reroute, you know, a different route. So let's say that, right, if a wire breaks, or yeah, if, let's say if a connection breaks, yeah, I'm going to say, right, connection slash wire, yeah, breaks or goes down, or yeah, becomes unavailable, right, let's say then the packets, yeah, the packets can travel along a different route, right, yeah, a different route, and yeah, I don't know, you could say like via an intermediate node, or yeah, via an intermediate device. Which obviously, well, yeah, I guess obviously you may think, well, that's not good for security, but I mean, yeah, I guess really, I mean, this data should hopefully be encrypted anyway, right? So in that case, they can't really understand what's actually being sent. Right, then we want to give two advantages of using a mesh topology instead of a bus topology. Well, of course, you know, the bus, well, this is going to have collisions, whereas, well, mesh, I mean, since we've got a direct connection, right, then we're not going to have collisions. So yeah, let's say that, I guess, let's say no collisions. Right, yeah, due to, well, yeah, let's say what, dedicated connections, or yeah, dedicated, and I think we can, let's say, right, dedicated full duplex. I mean, I guess it could be half duplex, but I mean, yeah, usually it's going to be full duplex. Right, let's say, yeah, dedicated full duplex, right, connections, right, between each device. I mean, you know, this, of course, you can also mention, well, it's going to be faster generally, like, again, because, you know, you've got a sort of dedicated wire just between two devices, whereas, of course, you know, the bus, well, you've got, like, all the devices just sharing the same wire, right, therefore it's going to be slow because, well, there's going to be collisions, right, they're going to have to wait. But I think, I mean, let's say the other one, so it's kind of redundancy. So I think, right, let's say resilient. Yeah, I think that's the word they usually use. Right, resilient. Yeah, I think, right, just check the spelling. Right, let's say resilient, right, because. So we want to say, well, if one line breaks, or yeah, if, let's say if one wire breaks. And I mean, this is what we just said anyway, right, the packets. Right, the packets can be routed. What a different, yeah, I know, maybe let's say along a different route. Yeah, let's say right along a different route, right, slash wire. Okay, the computers in one room are set up as thin clients in a client-server model. Describe the role of the different computers in this model. So of course, when we're saying thin client, well, this means obviously, yeah, I mean the client is sort of small, right? It's weak, and then yeah, the server is going to be, you know, the powerful one, right, doing the processing. So yeah, okay, let's say that, and I guess I mean the server in this case is going to be sort of the central device. Yeah, let's say maybe many. Right, so let's say many, I guess what, like small, or yeah, I don't know, sort of like low powered. Yeah, let's say, and obviously when we say low powered, we're sort of talking about resources, right? Not necessarily the energy usage. but yeah, just low powered in terms of let's say sort of I guess so, yeah, I don't know, kind of basic CPU, right? Not very powerful. Yeah, likewise RAM, probably limited RAM, right? Limited GPU, right? Many low powered right computers. And let's say right, we can say what will send their requests. Right, yeah, send right their request to a central server. Right, let's say yeah, which will do the processing. Yeah, let's say will perform the processing. Yeah, let's say maybe processing on the data. Right, and let's say yeah, and return it, or yeah, and respond with it. Right, respond with it. Okay, to the clients. And let's say what who will display, or yeah, I guess yeah, which, right, which will display it on their screen. I mean, yeah, hopefully that's going to be enough, right, display it on their screen. Like, let's try and add a little bit more, because again, it's always better to write too much than not enough. We can probably say what the client computers probably won't have much software, and also, probably don't store much of the data. Yeah, I think let's probably say that. Right, let's say the thin clients. Let's say yeah, have, I guess it's sort of, well, small amounts, right, slash no software or data. Right, okay, yeah, small amounts, right, slash no, right, yeah, software or data. All right, and then, okay, well, let's just say, right, the reason I say here, right, small, right, slash no, is because in some papers, they say, for example, this has no data, this has no software. And again, they kind of underline that, or yeah, well, I guess, yeah, they bold it as a keyword, right? Whereas in other papers, right, they say sort of limited amounts. And yeah, like in that case, they put that in bold. So that's what I think. If you put both of them, then yeah, hopefully they should accept it, regardless of actually what they have in the mark scheme. Okay, likewise for thick clients, right? Like, you don't necessarily want to say, well, thick clients do all of the processing. You could, so I guess for thick clients, well, again, you say, right, most, right, slash all, because again, it just kind of depends on the mark scheme, really. I mean, yeah, I don't know, like, I would hope the examiner would accept it, if you said most of the processing, but the mark scheme says all. Or yeah, likewise, if the mark scheme says most, but you said all, I mean, hopefully the examiner would accept it, but yeah, I guess who knows. Right, anyway, students can connect their devices to the university network using cables or wireless connection. Explain the benefits to the students of allowing them to use both wired and wireless. Right, so let's think wired, what that's going to be fast. It's also going to be, let's say, reliable, right, in terms of the connection doesn't drop. Well, it's going to be secure because, well, I mean, no one can, like, listen in, unless they have physical access to the wire, which, I mean, basically that means, cutting open the wire, sort of connecting to it, which is, yeah, not really practical. As opposed to wireless, where of course, anyone could just listen into the radio waves. Although of course wireless should be encrypted, hopefully. Yeah, well of course if it's password protected. And I suppose we can also say probably less interference. Right then, for wireless, we can think it's sort of more flexible, right? I mean, people can move around. They don't need a physical wire connected. Right, more, yeah, I guess what they can move is more convenient. Right, also different devices, for example, well, phones, tablets, which of course, yeah, you can't really use like a wired connection with a phone, since, I mean, well, obviously a phone doesn't have any ports for like a wired connection. Right, okay, so yeah, let's try and mention those, and I guess we need sort of 4 points for 4 marks. Right, let's say, well, it's here then we want to explain, right, so I've lots of detail. Right, let's say, yeah, wired connections will be faster. Let's say wired connections are usually faster than wireless. Right, and let's say and are also more reliable and more secure, or more reliable, more secure, less interference. Right, let's say and are also I'm trying to think how I can, structure it together in a sort of, semi sort of flowing way. I mean, all right, let's say, more secure. Right, since I guess all right, let's say, since eavesdroppers, right, would need physical access to the wire. And then I guess we can put in brackets, right, compare this with, right, to the wire. Yeah, I guess we can compare this with wireless. Right, let's say, maybe as opposed, right, let's say, right, to, I don't know, public radio waves. Or, I don't know, like publicly accessible radio waves or something. Let's say, right, publicly accessible wireless radio waves. Just to let them know that, of course, we know that, radio waves are wireless. Right, let's say, also, right, it's going to be, I guess, all right, let's say, also is more reliable connections will drop and, there's less interference. Right, also wired connections are more reliable. More reliable, right, and suffer from less interference, right, suffer from less interference, and we can say due to the dedicated, obviously, due to the dedicated wire, basically, or the dedicated connection. Right here, due to the dedicated connection. Right, and then now only a couple of lines left for wireless. Right, I mean let's say I don't know, maybe in contrast. Right, let's say wireless. Right, let's say is more flexible. Right, since it allows students to move around. I think let's say move around. Right, allows students, right, to move around, let's say, and still be connected. I guess here, I mean, you could mention, different rooms, but of course, they can go to the library, right, different classrooms, whatever. And I think, right, let's just mention, like, different devices like phones, tablets. Right, let's say also, devices. Right, let's say devices like phones or tablets. Phones, tablets, right, can connect. I guess to wireless. Right, let's say to wireless, right, but not wired. Let's explain why, right, since it does say explain. Right, let's say since they have, I guess, no. No internet wired connection or something. Right, since they have let's say no, or let's say like wired port. Let's say wired port, right, for I don't know, it's like network traffic. Because I mean, of course, things like phones and phones and tablets. I mean, of course, they do have like a wired connection. Say like a USB port, for example. But obviously, no port for like network traffic. Okay, then one site has split the network into several subnets or subnetworks. An IP address in a subnetwork is divided into two parts. Identify and describe the two parts of an IP address in the subnetwork. Okay, so what we can say then, there's going to be the network ID, then there's going to be the host ID or the device ID. And let's say if we've got a subnet mask of 255, right, 255. Right, let's say 255 and then .0, and let's say we've got an IP address of 192, right, 168, right, let's say .0, right, .1. Well, basically where we see a 1 in the subnet mask, or of course in this case 2, because I mean obviously 255 is just 8 ones. I think is that 8? No, 7. I think that's 8. So of course and here we've got 8 more ones, or 8 more ones, and then obviously just 8 zeros. So, okay, I mean basically, right, obviously where we see a 1, this means it's going to be the network ID. So that means, well, of this IP address, okay, all of this is the network. Right, then when we see a 0, well, this is the host ID. So of course this is saying, well, this is going to be device 1, right, on the network, 192.168.0. So yeah, let's explain that. Let's say, I know, yeah, maybe a network ID. And I think I'm maybe going to explain how this kind of relates to the subnet mask. Yeah, let's say subnet mask, right, bit, yeah, I guess what, bit value of 1. Because obviously, yeah, this was, like we said, right, where the subnet mask is 1, right, this is going to be the network ID. Right, and, all right, let's call it host ID. And let's say what, subnet mask value of 0. Right, yeah, are used, I guess what, to split the IP address. And then like maybe here we can just give an example, so similar to the one I said. What we can say that, I guess what, on a particular subnet, then, well, of course, right, I mean, okay, let's say all devices will have the same network ID, but of course it's going to be the, well, let's say the host ID or the device ID that's changing. Yeah, all right, let's say that. So on a subnet, right, let's say the network ID will be constant. Right, the network ID, yeah, will be constant for all devices. Or yeah, I guess will be the same for all devices. Right, yeah, while the host ID will be different for each device. Right, the host ID, yeah, will be different. Okay, right, for each device. Yeah, I mean, hopefully that makes sense. Okay, then a mobile telephone is used to record a video. The mobile telephone has a touchscreen. Right, there are different types of touchscreen. So before I try this, let's just recap the different types of touchscreen. Right, of course, well, one is going to be resistive, and what is the pen? Yeah, okay, the pen is working. Right, so there's going to be the outer red layer is conductive, I guess, yeah, as we can see here. Right, the inner red layer is resistive, so of course, right, this one here. Right, there's going to be an electric current constantly running between the electrodes. So yeah, I guess, well, just between these, yeah, I mean, between these layers. Right, when the layers touch, the circuit is complete. So I think really this is all you need to say, right? Yeah, obviously, well, when the top layer touches the bottom layer, right, that's where the electrics, well, obviously, yeah, that's where the electric circuit is going to be complete. Right, where the current will start to flow. Right, then we see the resulting coordinate is interpreted by the software. And right, yeah, okay, I mean, obviously, if we look at this, right, this is actually a soft screen. And like maybe people know, for example, let's say the Nintendo DS, right? The Nintendo DS, I mean, that would use a resistive touchscreen, because I mean, if people have actually had that, then of course, well, when you touch it, right? I mean, it's actually a soft screen. I mean, yeah, obviously, yeah, I guess, I mean, you can feel it. I mean, obviously, yeah, with the pen as well. Whereas, like, if we look at capacitive, well, this would be what, let's say, like a modern smartphone or a tablet would use. Then here, well, there's going to be an electrode, and again, that's just going to be, yeah, I guess kind of here at this layer. Right, this has a low electrical charge. Right, when a conducting material, e.g. finger, touches the protective cover, then a small amount of that charge is absorbed. So let's say here, I mean, what charge is in coulombs, right? So honestly, I forgot the physics. I think, is it Q is charge? Yeah, maybe. So I don't know, like, I'm just going to say like 1Q, like, yeah, maybe that's the completely wrong unit. I mean, I suppose current is going to be amps. So yeah, I don't know, okay, let's say 1 amp. Right, so here we've got, for example, 1 amp, right here we've got 1 amp. But then, right, where they touch it, well, right, some of that electric current is going to be like absorbed, well, in this case, into their finger. So of course, right, at this position, let's say the current goes down to, I don't know, maybe, 0.2 amps. And then, of course, I mean, well, the screen can then detect, right, where is the low current, and wherever the current is lower, well, that's, of course, where someone has, like, touched the screen. And, I mean, yeah, I think this one is not really required, but, for example, one advantage of capacitive touchscreens, well, one is going to support multi-touch. So, for example, you can also, like, touch here, and, yeah, of course, right, that's also going to be detected. Whereas resistive, okay, I mean basically it's only going to support one touch, right? You can't use like multiple fingers to, let's say for example, you know, zoom in, right, to swipe across, right, things like that. Another thing we say, well, capacitive is going to have a higher quality, right? It's going to look better in terms of, you know, like more HD. And the reason for that is, well, basically there's kind of less layers that are blocking out the light. Whereas resistive, yeah, I guess these layers are a bit thicker, right? Therefore it's going to block out some more of the light. And then, I mean, capacitive, well, you know, one problem with capacitive, like because anything that is conductive will work, then even, for example, water, like if you get water on a capacitive touchscreen, you know, let's say when it's raining, right, of course, well, like, I mean, well, then it's just not going to work, right, because let's say you're trying to type and, yeah, when there's water on the phone, yeah, of course, well, it's just going to press all the wrong keys, because in this case, well, some of the electric current is going to be absorbed by the water, and yeah, obviously the screen will think, you know, this water is your finger, for example. Whereas if we think resistive, well, because you actually need to apply physical pressure, I mean, well, the water droplet is not going to be heavy enough, right, to actually, you know, push the screen down like this. Yeah, that's why resistive is good for, let's say, factories, right? It's good for being used outside. It's good for being used in, yeah, let's say environments where obviously, yeah, the weather is not so good. Also where, for example, people need to wear gloves, right? You know, you can obviously touch it, right, even with a glove. Whereas capacitive, well, you would need some, you know, sort of special, like, let's say, electrically conducting glove, right, in order for it to work. Anyway, yeah, I think that was kind of a bit of a detour, right? So the mobile telephone has touchscreen. There are different types of touchscreen. Right, complete the description of the principal operation of a touchscreen. Right, a something touchscreen has two layers. When the user touches the screen, the layers touch, and a something is complete. So if this is talking about the layers touch, well, this was going to be the first one, right? This will be resistive. And then the thing that's going to complete, what we can say circuit, or I guess, yeah, maybe you say electrical circuit. Right, a something touchscreen, so I guess what this is going to be the capacitive. Right, yeah, has several layers. When the top layer is touched, right, there is a something in the electric current. So I guess what you can say maybe change or reduction. Yeah, let's say change, I think it should be okay. Alright, this one's going to be capacitive. Okay, right then, the last one, a microprocessor identifies the something of the touch. So I think here what you can say, like maybe position or coordinates. Yeah, I'd probably, let's say coordinates, right? It's a little bit more specific probably. But I think, I mean, position or location, I mean, yeah, probably that's okay as well. Right, the mobile telephone uses a built-in digital camera to record the video. The digital camera automatically focuses on the faces of the people. Explain how artificial intelligence AI is used by the camera to automatically focus on the faces of the people. Right, so I think, I mean, like actually often they don't want that much detail. Like they don't necessarily want you to talk about, let's say, like the machine learning model or, you know, neural networks, anything like that. Like if you just say, well, in this case, what it's going to be image recognition. So I think I'm going to say maybe an image recognition model, because I think, I mean, there's sort of no harm in being more specific than, yeah, sort of what they have in the mark scheme. Or let's say an image recognition model. And let's, like, I'm going to put in brackets, right, just explain how this works, right? Let's say, yeah, which was trained. Yeah, okay, right, let's say which was trained. Well, I guess by, you know, sort of loading it, or yeah, by, yeah, I guess, yeah, just loading it. Or, yeah, I guess, well, maybe processing. Yeah, let's say, right, processing. Let's say, I know, like lots, or yeah, huge numbers. Okay, let's say, right, huge numbers of photos. Right, let's say, yeah, both with and without faces. Right, and let's say what, to detect the difference, or yeah, to, you know, differentiate between them. Yeah, okay, well, let's say, right, to detect when a face exists or not. Right, yeah, when a face, right, exists or not. Right, so an image recognition model, okay, right, let's say is used. And I mean, to be honest, well, here we've got this, right? I guess what, to, yeah, detect. Right, so what, to detect a face as it's being. Yeah, alright, so I guess what, to detect a face, you know, within the frame. Yeah, right, to detect a face within the frame. And I guess what we can say, this process is continuous, right, since it's a video, right, maybe it's, I don't know, like 30 frames per second. Right, yeah, this process is continuous. Right, is continuous, right, and occurs for each frame. And I suppose, you know, when we say frame, like, let's just put in brackets image, because I mean, really, like, what a video is just, you know, a continuous, I guess, yeah, a continuous sequence of images, right? Like, if we've got like a 30 FPS video, well, that literally just means, you know, 30 images per second. Right, yeah, this process continues and occurs for each frame image. Yeah, I guess what, during the, yeah, I guess what, you know, during the phone call, or, you know, during the video call. Yeah, like, is there anything else we can say? I mean, I suppose what you could say, that it's going to stabilize, right? It's probably going to zoom in and stabilize on the face. Yeah, I mean, so let's maybe say that, right? So when a face is detected, okay, let's say the software, right, let's say, yeah, will automatically, right, let's say zoom in, right, / stabilize, I don't know, yeah, stabilize the motion on the face, or yeah, maybe like around the face. Yeah, I mean, so hopefully that should be enough for 3, I think. Okay, the video includes sound recording. Describe how sound is represented in a computer. So we can say, well, there's going to be, I guess, like a repeated measurements, and of course, well, I mean, I guess what the frequency of these measurements is going to be defined by the sampling rate or sampling frequency, and each of these measurements, well, I mean, of course, it's going to be an amplitude, and we say what the analog amplitude is then going to be quantized, and I mean, quantized just means basically, well, rounded to the, I guess, well, rounded to the closest digital value. And then, of course, yeah, well, I mean, each sample is then just going to be stored, right, sequentially in a file. All right, so yeah, let's try to say that. Let's say, all right, maybe periodic. Yeah, let's say periodic measurements. Right, periodic measurements, right, and actually, right, okay, well, let's put in brackets, right, samples, since, I mean, this is what it is. Right, periodic measurements, right, samples, right, yeah, of the sound, right, are taken. Yeah, okay, right, and let's say, yeah, and stored. I mean, I think, like, maybe I'll want to mention more about the sampling rate or sampling frequency. Right, so periodic measurements of the sound are taken. Yeah, okay, let's say, right, at a rate. Yeah, at a rate defined by the sampling rate. Or yeah, I guess at a frequency defined by the, you know, sampling rate. Right, defined, yeah, by the sampling rate. Right, and right, so I mean, here what we want to, we obviously want to mention the amplitude is, you know, sort of, well, again, it's quantized, right, or it's rounded to the sort of nearest, you know, digital value, or the nearest quantization level. Periodic measurements where samples of the sound are taken at a rate defined by the sampling rate. Yeah, okay, right, let's say, yeah, and the amplitude. Let's see what is, I guess, quantized. I mean, so quantized, I mean, basically just means, well, like rounded up or down. Right, quantized to the, yeah, let's say nearest quantization level. I mean, okay, well, I'll explain what this means, like, if you don't know what quantization level means. Right, quantization level, and I guess what we can say, like, yeah, based on the, because I mean, this one is going to be what, based on the sampling resolution. Right, and then I think then you probably say what, like, each sample is stored one after the other, or yeah, each sample is stored, you know, sort of in order sequentially. Yeah, okay, right, let's say, yeah, each sample is stored, right, in order. And let's put maybe in brackets, right, sequentially. Okay, right, so when we say quantization levels, I mean, well, in fact, I mean, here I've just actually got a picture of this. So in this case, like, if we see here, well, okay, I mean, here they call it bit depth. I mean, bit depth is also the same as sampling resolution. Now, in this case, I don't know, maybe let's say this is our value 0, this is 1, right, this is 2, this is 3, etc. I don't know, like maybe this is 16, for example. Now, of course, let's say if we're taking a sample, yeah, where is a good one where it's kind of in between? Yeah, I think actually like most of these are not that bad. Okay, so for example, like let's look at this one here. Well, in this case, this is kind of like probably about 2.6, right? So in this case, this is probably going to get sampled up to 3. Yeah, so in this case, of course, well, I mean, obviously, yeah, we have to round that up to 3, right? Since we can only store values 2 or 3. Whereas, you know, say if we look at the final one here, well, obviously, right, this has a lot more quantization levels. Therefore, right, because there's more quantization levels, or I mean, basically, what there's more values on the y-axis, then of course, well, let's say the rounding error, right, or the quantization error is going to be less. And of course, we can see that, right, both with the sampling rate, right, and also, well, the bit depth or the sampling resolution, right. When we increase both, then what the quantization error is going to decrease in both. Right. Therefore, of course, well, that means the accuracy is increasing. Which I think this is actually the next question. Right, so a second video is recorded. The sound in the second video needs to be more precise. Explain the reasons why increasing the sampling rate and the sampling resolution will improve the precision of the sound recording. So the sampling rate, we can say, well, obviously, I guess the time interval between each sample will be less, right? Therefore, we can like more accurately store the sound right at that current time. Yeah, and you say, well, obviously the quantization level, well, the quantization error will be smaller. Right, let's say, yeah, the time interval, right, between each sample will be reduced. Right, and then let's say, I guess, hence, yeah, let's say, right, hence the quantization, or let's say, yeah, the quantization error, right, will be smaller. Right, and then, well, let's say since, and I mean, okay, well, if we just go back here, I guess, I mean, obviously we're saying, I mean, it's kind of obvious, like, it's a bit difficult to explain, but of course we're saying, well, I mean, since the gap is smaller, then, yeah, I mean, well, obviously, right, it's just going to be more, you know, we can just more accurately kind of represent the value right at that current time. Yeah, right, hence, hence the quantization error will be smaller. I guess, yeah, since we can, or let's say more accurately, yeah, I guess like more accurately represent the amplitude right at that particular time. Yeah, I mean, I think this one is not a very good explanation. You know, probably check the mark scheme, right, see what they say. Yeah, I think most people can probably give a better explanation than this. Right then, anyway, if we think the next one, so the sampling resolution, well, this of course is just how many, well, again, I mean, how many quantization levels we have. Right, let's say, yeah, this will increase the number of quantization levels. And then probably let's put in brackets, right, what a quantization level is. Right, okay, and quantization levels. And I mean, basically what that's going to be the number of unique amplitudes that we can, you know, save, basically. Or yeah, I guess that we can represent. Right, so yeah, let's say, right, number of unique amplitudes, right, that we can represent. Yeah, I guess what, or that we can represent digitally. Right, yeah, this will increase the number of quantization levels. I guess what, hence, I mean, what, yeah, hence the, you know, again, it's just the same thing. Like the quantization error will be smaller. Right, hence the quantization. And in this time, like, I'm maybe going to just put in brackets rounding, because I mean, obviously, yeah, this is just what it is. Right, rounding error. Yeah, will be smaller. And I suppose what we can say, right, since there's a smaller gap between each quantization level. So of course, rather than say this one being, I don't know, like 2 decibels, this one being 3 decibels. I mean, obviously in reality that's super quiet, right? So maybe, I don't know, maybe let's say like 60 decibels and 61 decibels. But of course we would have, 60.001, or 60.002. So of course, we just got kind of much more levels. Right, since there's a smaller gap right between each quantization level. Alright, and then the next one, a shop rents cars to customers. The shop uses a relational database to store information about the rentals. Describe 2 ways in which a relational database addresses the limitations of a file-based approach. Right, so one, they often mention this, it's called program data, or it's going to reduce program data dependence, or program data interdependence. So, okay, let's just write that and then I'll explain. Right, so reduce program data, let's put a hyphen. Right, let's say interdependence. Right, dependence. Or I guess let's say since. Right, so I mean what we're saying then is let's say if we have a file, and if this is like a text file, right, a file-based approach. Now maybe, for example, I don't know, we have some file about like games, for example. Now maybe the game, right, we're gonna have a title, let's have a price, let's say we can have description, maybe an age rating, I guess like maybe some genres, of course, right, etc. Now the problem with this is, well, let's imagine now we want to add a new if we want to add a new field, right, of course, well then we need to actually go into of course we have to go to our code, right, we have to update our code, so that of course now, like, rather than expecting say like 5 columns, right, we're going to expect 6 columns. Of course we have to handle that new field correctly. We need to extract the data, we need to check the format is correct. Of course, right, there's a lot of interdependency, right, between the actual file structure, right, and our actual code. There's the I guess the code that's gonna let's say sort of insert new data, right, that's gonna update the file, that's gonna query the data, right. So I mean it's not just one bit of code, right, it's going to be for all parts. I guess all of the sort of CRUD operations, right, which that's going to be select, update, insert, and delete. Of course, right, the code for all of those needs to get modified. Likewise, like probably deleting would be even more annoying. Like if we're going to sort of delete one of these columns, right, or fields, right, or for example, maybe we need to change the data type, right, or we need to expand one of the columns. Like let's say maybe we had this description could have been a varchar of like 100, but now suddenly there's a game with a description of 120 characters, right? Then of course we need to modify the definition. Whereas of course if we're just using a relational database, well then it's quite easy, because of course we can just use I guess what they call it DDL, right, data definition language, or is it I think data, or maybe database. I guess something definition language, I think it's data, right, maybe database. So I mean what that means, basically just create table, right, that's going to be the I guess the sort of statement, right, in order to create a new table. And then like obviously if we want to update the table, well then we're just going to use like alter table add column, or I guess alter table modify column. And of course, like in this case, let's say the DBMS is just going to handle like the actual file storage on disk for us. Obviously we don't have to sort of do any of that, right, that's all going to be abstracted away from us. So let's just say that right, reduce program data independence, right, since I guess let's say the DBMS, the database management system, right, abstracts let's say, right, the complexity, or I guess the sort of file storage complexity. Right, file storage complexity, I guess away from us. And I guess I don't know. I guess we could mention, right, we can use DDL to like easily create and modify tables. I guess maybe, right, it provides, or I guess they provide, right, it provides us, right, with an easy way yeah, to, I guess, let's say create new tables. I guess modify, or I guess, yeah, sort of new table definition, right? I guess, yeah, modify table definitions. Right, let's say etc. Or let's say, yeah, via, right, DDL statements. Okay, and then I think for 2, I mean, you could mention something like, say, referential integrity. So, I mean, like, okay, 1, they also say it's going to be easier to do complex queries. But I feel, here we've kind of mentioned why it's an easy way to, sort of create new tables, modify table definition, right, etc. So I don't really want to say, something about queries again. But of course, you can say, well, it's going to be easier to do complex queries because, again, right, all of the complexity is abstracted away from us. Like, we can just do, I don't know, yeah, let's say like select, right, then we have the column names, all right, then we say from, then we say the table name, or yeah, relation name, right, then we have where, and of course we can have a list of conditions, right, then we can have order by, right, group by, yeah, of course, right, things like inner join. Now, you imagine if you had like a text file and you were trying to do all of that, right, of course you'd have to, read the whole text file line by line. You would then want to, you of course want to filter out the rows that don't match. You would then want to sort them. You'd want to, put them into groups. Yeah, it's just going to be really complex. And the thing is, of course, right, you would need different code for each different, for each different query. And of course, that's going to be, I mean, it's not going to be short code like a short SQL statement, which is, sort of like one line basically. Yeah, it's going to be, quite a long program, right, to actually filter, to sort the data, right, to group the data. So yeah, I mean, you could say that, but I mean, since I kind of mentioned that already, like let's probably talk about the data consistency. All right, so let's say, right, improves data consistency. I guess what we say, due to ease of normalisation. Right, let's say ease of normalisation. Right, normalisation and I guess, right, and joining tables. Or joining relations. Right, let's say joining tables, right, in queries. And I mean, what we can also mention, for example, referential integrity can also be used. Right, referential integrity, right, can be used. And what this will be to automatically delete data that, okay, right, let's say to automatically delete data that has been, okay, all right, okay. Well, let's say to automatically delete data that references a primary key that has been deleted. And I'll give an example of that in a minute. Right, reference, okay, yeah, let's say, right, can be used, right, to, right, automatically, right, let's say, I mean, not delete data, let's say maybe delete, tuples or records. I mean, right, I mean, a tuple, right, that's just a row, right, row record. Right, delete tuples, yeah, which have a foreign key. Right, a foreign key, I guess linking or referencing, right, let's say linking to a primary key that has been deleted. So of course, this means, well, I mean, it's something called like orphaned nodes, right? We're not going to have an orphaned node. So to give an example of this, I mean, I think, right, I'm just going to go with a simple example, like I usually do. Right, let's say you have a website. I think, okay, let's say we've got users, and you could have, right, posts or comments. Now, of course, well, let's say the user, right, of course, well, they're going to have a user ID, right? Let's call it UID. I guess, I mean, the user ID, that can also just be the username. Right, of course, they're probably going to have like an email address, right? They're going to have, I don't know, maybe some other things. Right, a post, well, right, that's going to have, I guess, probably a post ID. Right, you're also going to have a user ID. And in this case, the user ID, because, well, of course, right, this is the author. Right, this is going to be a foreign key, right, to, obviously the user primary key in this case. Of course, what the post is going to have, title, it's going to have, I guess, description, right, content. Same for comments, of course, what you're going to have a comment ID. Then, well, again, you're going to have the user ID, right, the author ID. Now, let's say that we want to say, well, when a user deletes their account, or I guess when the user has their account deleted for I don't know, some like violation or something, right, then we want to automatically delete all of their posts, right, and automatically delete all of their comments. Now, if you set up a referential integrity rule, and in MySQL, I think it's like on cascade, you'd want to set up, I think on cascade delete, right? I mean, this is what you add inside the create table statement, and this is going to be on the foreign key that you want to delete, right? When you add the foreign key. So what we say is then, well, right, if a user gets deleted in this table, right, then the corresponding, let's say the corresponding post, right, by that user, right, are also going to get deleted. Right, likewise, of course, right, any comments by that user, right, they're also going to get deleted. So hopefully people can understand, right, why that's going to sort of improve data consistency, because otherwise what you would have is, well, you're going to have a user that doesn't exist, right, but a post that does exist. So it's just going to say, well, like post, from unknown user. Obviously, likewise, right, same for comments. Right, then complete the table by writing the missing term or description for each database feature. Right, an object that data is stored about. So this will be just, for example, what like user post comment. And if we think this is just going to be called an entity, right, because of course, if you think, let's say, entity relation diagram, well, in this case, right, let's say we have user, we have what post, and we have comment. Well, let's say what one user can have many comments, and of course, right, this is the entity relation diagram. And of course, I guess, well, let's say one user can also have many posts. And then in this case, you'd also probably want to say that what one post can also have many comments, because of course, people can actually reply, right, to the post. Right, then tuple. So I mean, a tuple basically is a record. I guess record, right, slash row. Now, I mean, like probably you can just say row. Like I think sometimes they're a bit more specific, and they say what is the data about. Okay, I guess you can say it's the data that is uniquely identified by each primary key. Because I mean, if you think, right, that's what a row is. Like, okay, let's say you have, I know, user 1, user 2, user 3. Well, of course, the data is going to be uniquely associated with a particular primary key. So okay, let's write all the. Okay, all right, so what I'm going to do, okay, well, let's go with the simple definition. Let's get a row, right, in a relation. Right, okay, let's then give the more complex definition. All right, so let's go i.e. Right, all of the data, right, in a, in a relation, right, associated with each primary key, or with a primary key. So obviously, I mean, a primary key has to be unique. Now, you couldn't say associated with a foreign key, because in theory, well, I mean, of course, you can have a foreign key that's repeated, right, in a relation. I mean, if we just go here for an example, well, of course, here, right, we can have many posts by the same user, right? We can have many comments with the same user. So it's going to be, like, user ID 1, user ID 1, but, comment ID 1, comment ID 2, comment ID 3. So, of course, right, the primary key has to be unique, whereas, a foreign key doesn't have to be unique. Right, then, secondary key. So I think the secondary key, that's going to, I mean, like, honestly, this is often just called an index as well. So an index, I mean, this is something we can sort of easily search by, or we can, search, sort, group, right, all of those, like all of those operations we can do quickly. And the reason for that is, well, because we've created an index, right? So the way it's stored, I mean, well, basically it's using something called a B tree. I mean, it's kind of similar to a binary tree, right, which people may be familiar with. If you've never heard of binary trees, well, it's going to be an A2 thing. Okay, I mean, well, basically it's a data structure, right, just like a stack, a queue, a linked list, right? There's also binary trees. So I mean, it's going to be fast, right? Since we've created this additional structure to make it fast. But I think what we want to say, maybe, right? I guess maybe another field, or okay, you could say another candidate key. Because if we think, well, a candidate key is going to uniquely identify a tuple, or I guess uniquely identify a row. Right, another candidate key. Right, that wasn't, I guess, that wasn't chosen to be the primary key. Yeah, and okay, well, let's say, right, can uniquely identify, right, uniquely identify any tuple. Right, uniquely identify, yeah, any tuple. So an example of this, okay, let's say you have, I don't know, a person, and I mean, okay, well, let's say person entity, and in this person entity, well, maybe you want to store a couple of things, right? One could be, let's say, their passport number, and in this case, well, let's say their passport number, right, that can be their primary key, but then you could also have, for example, email. Now, right, email, that should also be unique. So in this case, like email, I mean, yeah, okay, an email is going to be a candidate key, okay, because of course, well, yeah, this could also be, sort of used to uniquely identify this person. But in this case, since we've actually chosen passport to be the primary key, right, then that would make email a secondary key. Likewise, of course, you could have, for example, phone number. You could have, I don't know, maybe social security number. Yeah, of course, right, many different things. Right, the car rental database is not normalized. The current database design, right, booking, that has a car registration. So I guess, right, that's going to be the primary key. In fact, actually, okay, so this is going to be a composite key, because I guess the primary key is going to be what the car registration, yeah, probably the start date and end date. Okay, so if you have all three of this information, like I guess that's going to be unique. Right, and then what's going to be the car model, the car color, and the customer first name. Right, then customer, that has customer first name, customer last name, right, email address, and telephone number. Okay, we want to write a normalized. So of course, when it says normalized, what this means, right, 3NF, right, fully normalized. Yeah, third normal form. Right, designed for this database. Okay, well here it tells us then. Right, all the field names given, right, and underline, yeah, the primary key fields. Okay, so I guess here, well, we're also going to want another table, right, another relation, which is going to be car, because what car is there going to have, let's say the car model, right, and also the car color. Yeah, so I think let's just write this one first, because this one's quite simple. Right, so that's going to be car model. And in fact, actually, all right, yeah, maybe this is not so simple. Right, it's going to be the car registration. Right, that's going to be the primary key. Because of course, you can have like many cars that are the same model. Yeah, this is going to be what the ID number or something. Yeah, I guess what the license plate. Right, then the car model. Yeah, let's just underline this, right, since it's the primary key. Right, then the, well, I guess, car color. Yeah, that should be all we need. Yeah, okay. Right, then if we go, let's go customer, because I mean, yeah, right, big letters. And I mean, okay, so for me, the reason I'm doing this first is because, well, these are kind of like distinct entities, right? They're not going to have to be linked with anything. Yeah, I guess, I mean, well, they don't have foreign keys, basically. Whereas, booking, this is a bit more complex because, obviously, right here we've got a, yeah, car registration foreign key. Right, we've also got a customer first name, which I guess is probably going to be a customer ID, yeah, foreign key as well. So let's think for customer. Well, the thing is, I mean, the first name and last name, like, they're not really going to uniquely identify a person because, of course, well, I mean, yeah, there's going to be many people with the same name. So yeah, I mean, let's go customer ID. Right, we can make a new primary key. All right, customer ID. Yeah, that's the primary key. Like, right, I'm not going to write the whole thing because it's too long. Let's go FN. Right, that's first name. Right, let's go LN. I mean, of course, yeah, in the exam, you should obviously write the whole thing. All right, let's get EA, right, email address, and I guess, right, TN, telephone number. Right, then let's think booking. So, right, okay, I mean, how can we uniquely identify a booking? I guess what one can be, I mean, I guess what one you're going to need the car registration. And then, yeah, I mean, I suppose we can just keep it the same, right, car registration. So, right, let's call that CR, right, car registration. Yeah, I mean, let's go start date. And I think most of this we can keep the same, right? So start date, end date. And then let's say, right, this will be a composite. Yeah, okay, let's say this will be a composite primary key. And then, well, I mean, so the car model, car color we don't need, right? Since we can get that here based on the car registration. And then the customer, well, here, right, let's go CID, right, the customer ID. And again, of course, in the exam, write out customer ID fully. But yeah, I think that should be okay. Right, the data is validated and verified when it's entered into the database. The car registration number, right, must be one letter followed by three numbers followed by two letters. Right, for example, A123AA is valid, right, but A12AA is invalid, right, since I guess, yeah, one needs to be followed by three numbers, right, this only has two numbers. Right, one way that a registration number can be validated is by using presence check to make sure the registration number has been entered. Right, describe two other ways the car registration number can be validated. So I think this one, I mean, well, the easy one is just format, right, because, well, you know, honestly here, right, the format is one letter, three numbers, two letters. So let's say format check. And yeah, like this one, it seems a bit silly because you're literally just repeating the question. Okay, I guess, well, let's say, right, should be, or yeah, data should be, yeah, I guess, well, just data should be, let's say, what, one number, right, yeah, then, okay, right, sorry, right, one letter, right, okay, then three numbers, yeah, then, right, two letters. And then if we think about this, I mean, this is actually just going to be a constant length because, well, of course, right, 1 plus 3 plus 2, well, that's going to be 6. So, right, let's go length check. Of course, you know, length check where you can check, right, if it's exactly equal. Of course, you can also check what is the length greater than or equal to something. Yeah, you know, and maybe less than or equal to something, right, if it's within a range. Yeah, it's kind of like a range length check, I guess. Right, so length check, well, I guess ensure. Yeah, right, ensure car registration. Right, car registration, right, consists of 6 characters. And I think, I mean, if you think about, say, SQL, right, when you create table, well, for this, right, you'd want to go what varchar, and then I guess 6. Or actually, in this case, this is actually not going to be a variable length character. So yeah, here you could actually just go char. Right, because if we think, well, char means it has to be 6, whereas you have varchar, well, that means it can obviously be less than 6, right, but a maximum length of 6, because, well, varchar just means like variable, right, so variable length character. Right, then describe two ways the car registration number can be verified when it's entered into the database. Okay, so let's go, I guess, what, double entry check. So this is where what the system will ask to enter the thing twice. You know, kind of like when you sign up for a website, right? It says type in your password twice. Of course, and yeah, what the system is then going to check, right, that they match. So look, right, let's say system. Yeah, I guess requires. I guess what requires registration to be all right, let's say car registration number. Right, to be entered twice. Right, to be entered twice. Yeah, and let's say, right, and ensures they are the same, or yeah, ensures they're equal. Right, ensures they are the same. Right, and then I guess what the next one is just visual check. And let's say what the person, and you know, for this, right, you can also say, well, it can be the same person, it could be a different person. So let's say the person, right, let's say the person, sorry, / a colleague. I guess what will manually, yeah, look at the data to make sure it looks correct. Or let's say, yeah, we'll manually compare. I guess what compare the data entered. Yeah, I know, like with their physical record, because you know if it's been like written down on paper. Right, physical record, yeah, to make sure they're the same. Right, okay, then state why the car registration number might be incorrect even after it's been validated and verified. So, I mean, well, basically you just think, what, like a typo? So, yeah, of course, what, it can be the correct format. And I guess, yeah, maybe they, you know, they look at it twice, right, they still think it's correct. But of course, yeah, if they make the same sort of typo mistake, right, then of course that's going to be, yeah, invalid. So yeah, I mean, maybe let's say like an incorrect. Yeah, okay, right, let's say, yeah, an incorrect. Right, but I guess sort of, yeah, I don't know, sort of like valid format, or yeah, like valid. I mean, maybe validly formatted. right, validly formatted, car registration number was entered. And I guess, I mean, here you could also say, I don't know, maybe it's like out of date. Although I suppose a car registration number is not really going to update. Like, and yeah, I guess unless someone pays for a sort of personalized one. Yeah, okay, I mean, maybe let's say that, right, e.g., yeah, out of date. Let's say out of date data. Yeah, I guess what, I guess comma, right, yeah, or typo. Or yeah, you know, typing mistake. Right, a programmer is developing a computer game in a high-level language to sell to the public. The programmer uses both an interpreter and a compiler at different stages of the development of the program. Explain the reasons why the programmer uses an interpreter while writing the program code. Right, so here then, they always just like to mention debugging. Right, let's say, yeah, easier to debug, or let's say easier and faster to debug. Or let's say since. Right, since if an error occurs. Right, if an error occurs, I guess, yeah, or let's say the program will crash. Well, yeah, well, I guess, yeah, the program might crash. Okay, oh, yeah, well, let's say will. Right, the program will crash. Right, the developer, right, can modify the code. Yeah, and code, right, and let's say, yeah, I guess, and resume execution from that point. Whereas, of course, you know, if it's compiled, what you have to, yeah, recompile the whole project. Of course, it's going to run from the beginning again. Right, I think another thing they say, what you can execute just parts of the code. So let's say, for example, you know, you just have, like, I don't know, sort of a couple of functions, and yeah, maybe you only want to sort of, you know, execute this one particular function or something. Yeah, then of course you can just do that, right? You just sort of, yeah, copy that code that you want to execute. Yeah, then just paste it into the interpreter, right, just to test it. So let's say, yeah, portions, yeah, or parts, right, portions of the code. Yeah, I guess what can be selected, right, can be selected, right, slash pasted, right, pasted into interpreter. Yeah, I guess what, to easily test, you know, that particular part of code. Yeah, I guess what, to easily test, right, I guess, yeah, those statements. And of course, again, you know, if there's any error that's found, well, of course, you're just going to, you know, directly modify some of those lines, right? You know, of course, yeah, just, well, modify until it's working. So yeah, it's quite, you know, quite easy to test, right, quite quick. Right, then explain the reason why the program uses a compiler when the program has been written. Right, let's say a compiled program is easier to distribute, since in this case you don't need, well, I mean, you also don't need the user to have the interpreter installed, right? Or you don't need to ship the interpreter, you know, with the software, yes, or when they, yeah, when they download it. Right, a compiled program, or I guess what, compiled game, right, I guess, yeah, is easier, right, and more convenient to distribute. Yeah, since, right, let's say, yeah, since user, right, or well, maybe, right, since end user, right, isn't required, yeah, to have / download the interpreter. Right, I guess, well, let's also say faster, right, so a, yeah, I guess also, right, also, yeah, what, the compiled code will be faster. Right, the compiled code will be faster. I guess what, since, and I guess, yeah, since says explain, right, since it's already machine code. Yeah, I guess, right, since it's already machine code, I guess what, you know, can directly, yeah, I guess, right, let's see, right, and can directly execute. Yeah, that's right, can directly execute without, Okay, right, without, and let's say without runtime translation. And then I think another thing, right, since there's three, we can probably mention, like, let's say privacy, right, it's going to be harder to reverse engineer. So let's say kind of what, like, yeah, I probably want to say about, like, intellectual property. So kind of like easier to maintain intellectual property. Yeah, all right, okay, well, let's say harder, right, for users to reverse engineer. Right, to reverse engineer. Yeah, reverse engineer, I guess sort of, also like modify the game, right, so they can, cheat and things. Right, harder for users to reverse engineer, right, yeah, I guess see the source code. Right, let's say hence, yeah, intellectual property. Right, intellectual property of company. Yeah, I guess right, of company, like, is like, it's probably not the best, but I guess just easier to maintain. Yeah, there's probably a better way to say that, but yeah, hopefully that makes sense. Right, the programmer needs to publish the game under a software license so that it can be sold to the public. Identify the most appropriate type of software license for the game and justify your choice. Right, so here I'm just going to say commercial. I noticed they do actually accept shareware, right, if you look in the mark scheme. And for shareware, what they say is that, well, of course, right, you can distribute like a free demo, yeah, to, obviously, well, to the players. And then the advantages of that is, of course, well, hopefully lots of people will play the demo, right, since it's free. And then if you get, obviously some of those people then go on to buy the full game, well, that's obviously going to be an advantage. Whereas, like, if you have, I know, some, expensive game, well, a lot of people are not even going to try it, okay, they're not even going to buy it. But yeah, I think for me, like, I'm just going to say commercial is probably, just easier, right, since they're talking about, yeah, selling it to the public. So I guess what this, yeah, I guess this maybe prevents, let's say, right, prevents users, yeah, from, well, let's say legally distributing, I guess distributing, modifying, yeah, or reselling the game. Right, yeah, distributing, yeah, I guess modifying, right, or reselling the game. Well, I guess, yeah, in order to protect the company's intellectual property. Yeah, right, in order to, right, protect, right, the company's, right, the company's intellectual property. I guess, let's say, right, this license. So we can say, this license provides a legal kind of grounding, of which they can, obviously sue someone, right? They can take legal action, I guess. Yeah, okay, right, so this license, I guess, yeah, provides, right, a legal, I guess, let's say legal basis, right, that a company can use. Right, a company can use to take legal action. Yeah, let's say against, I guess, yeah, infringing parties. Yeah, I mean, well, let's think, right, is that enough for 4 marks? So I think commercial, I mean, that should be 1. I mean, prevents users from legally distributing, modifying, or reselling the games. Yeah, I mean, hopefully that's going to be at least 1, right? Maybe 2. And then I think what's saying maybe a legal basis that they can, sue the people. Yeah, I mean, hopefully that's going to be enough, right? So I think hopefully that's going to be 4. Right, data needs to be kept secure when stored on a computer and during transmission over a network. Explain how a digital signature is used to authenticate a digital document during transmission over a network. Okay, let's just try and explain this then, because this is a super complex question, especially since in the book they actually say this is not required until A2. Right, then what we're going to have, okay, there we go. Right, let's say we have the document, okay, this, I don't know, just ABC, right, some simple text. And to be honest, I'm probably just going to create another copy of the document, yeah, just for sort of visualization purposes. Right, so this first one we're going to hash. and yeah, let's say this is a function, right, put it in brackets. And if we think, well, a hash function, this is going to take an input, and based on the input, well, okay, well, let's say if we have the same input, right, then the same input will always produce the same output. So let's say, for example, I mean, of course, this is not true, right? It depends on the hashing algorithm. But let's say ABC, you know, in our hashing algorithm always produces, and then let's say like Y8T, right? That's going to be the output. And here they actually call this a hash digest. So yeah, the hash digest is just going to be this, right? The output. And of course, yeah, any ABC input, right, always produces the same output. Right, then what we're going to do, well, we're going to sign this, right, the digest. And in order to sign it, well, let's actually create our two people, right, A and B, sender and receiver. Now, both of them, A is going to have a public key, A is also going to have a private key. Likewise, B is also going to have a public key, B is also going to have a private key. And notice, right, these four keys, they're all going to be different, okay, they're all distinct. It's not like symmetric encryption where they're using a shared key, right? In this case, yeah, the four keys are all different. Right, okay, so yeah, okay, well, that right here, then we've got this hash digest, right? Then we want to sign this, and the way we sign it, well, we're going to use A's private key in order to sign. So yeah, okay, right, I'm just going to put S, right? So S just means sign, right? Okay, let's say, you know, when we sign this, right, this is obviously going to go to some other data. Yeah, you know, it doesn't really matter. Maybe let's say F. Yeah, I know, like F, right, D, 3 or something. Yeah, obviously it can be anything. Right, so then what we're going to do, okay, we're going to take this digital signature, right, and also going to take the original document, okay, then we're going to send both of these. And to be honest, you know, we can probably encrypt these as well. So if we're encrypting, well, we're going to be encrypting with B's public key. So notice, right, that when we're signing and then, well, you know, correspondingly, we're going to verify. So right, sign and verify is going to be using the sender's keys. Whereas when we're encrypting, well, then we're using the receiver's keys. So, right, okay, let's say in order to encrypt, we're using the receiver's public key. Right, okay, so, well, then of course we send this to B. Right, B gets this. Now, in order to decrypt, well, B is going to use its private key, or yeah, the receiver will use its private key to decrypt. Right, then what they're going to have, so then I guess what they want to verify, yeah, they want to verify this signature. So the way they're going to do that, well, they're going to use A's public key in order to verify the signature. Right, this will then get, or I guess we can also say, you know, to kind of decrypt. Right, at this point then they have this sort of Y8T. Right, so this was the hash value. They're also going to have ABC. Because of course, what ABC, I mean, well, basically it's just encrypted, you know, inside this whole message. But of course, yeah, what we've decrypted using B's private key here. So now what we can do is, well, of course, right, we can then hash ABC. And when we hash ABC, well, we want to check, right, does the hash equal, right, the hash that they've told us? And of course, if it does, well, right, then we know, one, it's from this person. And the reason we know it's from the person, right, so I guess the authenticity, I guess we're kind of authenticating the person. So we can authenticate them because we know that, well, like only the person with the corresponding private key, you know, will the actual decryption work, or yeah, will the, you know, sort of verification work, right? So yeah, I mean, we can say, well, I mean, since we were able to successfully verify, right, using A's public key, right, then basically, obviously, well, that, I mean, yeah, I guess that must have been A that signed it, right, since, you know, only A has the corresponding private key. Right, likewise, we can also check the integrity. Because we can say, well, if, for example, if we hashed ABC, and let's say our value equals, I don't know, like, let's say Y8, I don't know, what's after T? Yeah, well, let's say 9, right, Y89. Well, of course, you know, this is not going to be correct because, yeah, obviously the hash value they've got, or well, the hash value they said is not equal, right, to the hash value we expect. Yeah, I mean, I'm going to try and demonstrate this here because I think with an example, it's actually easier to understand. So let's say, I mean, you can use this website, PGP tool. I mean, there's also many other websites, right? Type in, you know, online encryption, right? Online, yeah, hashing, right? Yeah, online, you know, sign, verify, right? There's, yeah, obviously many websites. Right, I've gone ahead and just filled in the details, right? Let's go generate keys and also generate keys here. Right, I mean, I've just used 1024 bits. I mean, this is a, you know, short key, but right, it's good for testing. It's going to be fast. Right, then what we want to do, so we're saying, right, this person here on the left, this is the sender. Now, what we want to do, well, let's take our document and right here this is what this is just going to hash right using the secure hashing algorithm. Right, then 256 means what, 256 bits. That's going to be the length of the digest. Now let's just say our input, I don't know, let's say like hello world, right, something simple. So we see, right, this is then the hash digest. Then what we want to do, we want to go here to encrypt and sign. Right, we're going to get, right, so our message in plain text. Well, in this case, I mean, let's just send the hash digest. Yeah, since we just want to sort of verify. Right, so then we, the signer's private key. And as we saw here, hang on, not this one. Right, so the signer's private key, that was going to be A. Right, and that's what we were doing here at this step. Okay, no, sorry, yeah, well, that's what we're doing at this step here. And we said, well, this FD3, right, this was going to be the output. So let's just go ahead and just copy that. And, right, yeah, this is, okay, so this is the sender's private key, effectively. Right, then we want to get the receiver's public key. So the receiver, okay, that's this person. And the reason we need their public key, well, this is for encryption. Yeah, I guess specifically, right, asymmetric encryption. Right, and then, yeah, that's all we need. So then if we just go, what, encrypt. Right, signing out incorrect password. Okay, alright, so yeah, here I need to type in the password. So for me, I just set the password, right, ABCD, or yeah, ABCDE. Right, okay, yeah, so now it's been, what, I guess, signed and encrypted. Right, then if we take this and, right, then let's go on the receiver. So the receiver we want to decrypt and verify. Right, so we just paste the encrypted message here. Right, then we want to use the signer's public key. So the signer's public key, this is for verification purposes. But I guess first, like before you can verify, well, first you actually have to decrypt. So let's copy our private key, which is going to be this one here. Right, yeah, then, so the signer's public key, right, this was for verification. So, right, hang on, it was, yeah, this one here. You know, as you can see, right, it's quite complex. You have to, yeah, make sure to copy and paste, you know, the correct thing. Like, obviously, like, if, yeah, I mean, obviously, well, if this was, you know, in real life, right, it's just going to happen, like, automatically in the background. You know, of course, yeah, you don't have to worry about doing any of this. Right, then if we just go decrypt, and yeah, it says, right, messages decrypted. Right, yeah, signature is verified successfully. Right, and then, so we see here, well, this is our hash digest. And if we actually compare this with our original hash, right, well, we see, of course, right, these hashes match. Right, therefore, that's how we can tell that, of course, yeah, the data is being sent correctly. Yeah, well, the data is being received correctly. Now, if, for example, you know, this was a real email, well, then, as well as sending the digital signature, right, we would, of course, actually send the real document as well. Right, yeah, then, of course, you know, we could compare. But yeah, I mean, since, you know, in this example, right, we're just sending the signature, right, we're not actually sending the document as well. So yeah, I mean, let's just try and write all of that, because again, this is quite complex to explain. So we can say maybe first, right, let's say, yeah, first, what the, let's say the document, right, the document is hashed. Right, I guess what hashed, maybe, right, using, yeah, I don't know, like using a hashing algorithm, right, to produce a hash digest. Right, then let's say, I guess what, using the, so yeah, okay, let's think, right, okay, using the sender's private key, and, yeah, alright, okay. Like, I was going to say, alright, using a hash digest, maybe, right, to ensure, I guess what, to ensure integrity, although I suppose, yeah, here it's really talking about authentication. Yeah, but I guess, I mean, you also want to ensure integrity, right, ensure it's not being modified. Yeah, okay, right, to ensure integrity. Right, then what was I going to say? I guess, right, yeah, I guess maybe next, or let's say next, right, the digest, right, is signed, right, with the senders, right, with the sender's private key, right, let's say, yeah, and encrypted, right, with the receiver's public key. Yeah, okay, right, receiver's public key. And you know, some people think, well, like, how do you remember, like, when is it the receiver, when is it the sender, when is it the private key, when is it the public key? But just remember that for signing, well, signing is always going to be the sender, right? Whereas for encryption, right, it's always going to be, you know, the receiver's keys. And of course, you know, if you think, well, I mean, obviously, like, the person is not, well, the person is never going to have access to the other person's private key, right? Therefore, of course, when we're signing, well, if we're using our own keys, right, then of course, well, that must mean, you know, we're using our own private key, right? Likewise, you know, of course, well, when we receive the when we receive, you know, the ciphertext, right, the encrypted message, well, then of course, you know, that means we have to decrypt, right, using our private key. Yeah, since again, you know, obviously the person is encrypting using our public key, right? I mean, since they don't have access to our private key. Yeah, I mean, hopefully that makes sense, but like, if it doesn't, again, just, you know, use some online tools, right? Have some exam, or, you know, have some practice, right? Doing this yourself, right? Encrypting, decrypting, signing, verifying. Right, okay, so encrypted with the receiver's public, yeah, I said public twice, right? Public key. Yeah, I guess, and transmitted to them. Right, let's say, I guess, what, yeah, upon receival. Right, so let's say, yeah, I guess, what, upon receiving. Right, let's say the receiver, right, will decrypt with their, decrypt with their private key. Right, decrypt with their private key. And I might actually say, right, so, okay, let's say the digest, let's actually sort of have a line here. Or let's say, yeah, digest and document, right, since this is going to be both. Yeah, the digest and document. Okay, well, I guess, yeah, okay, that's fine, I think. Right, upon receiving, the receiver will decrypt with their private key. Right, and let's say, and verify. Right, using, or I guess, right, let's say, right, verify the digital signature. Right, okay, yeah, using, right, the, okay, what, using the sender's public key. Right, let's say, yeah, I mean, what if verification was successful? Right, then we know, or I guess, yeah, I guess what, I mean, this authenticates, I mean, since, I mean, let's use this word here. Right, I guess what, this authenticates the sender. Right, the sender, yeah, since, right, only the person with the corresponding private key would be able to produce the digital signature that, you know, that we can verify with that public key. Right, since, yeah, I guess, right, only, right, the person, right, with the, yeah, I know, right, with the corresponding, right, corresponding private key, right, yeah, would have been able to, right, would have been able to, I guess, yeah, sign the original document. Because of course, what would happen, like, okay, let's say if, I don't know, maybe you have some, like, different private key and a different public key, right, or obviously keys that are not matching. Well, like, if the keys are not matching, right, if they're, you know, some random keys, well, then you're going to get an error, right, when you try to verify it. Yeah, that's why, of course, right, the keys have to be related. Yeah, I mean, so hopefully that makes sense. But again, I think, you know, most people would probably just get like 1 or 2 marks on that question. Like, especially since, again, you know, in the book they say you actually don't need to know that for AS. Right, anyway, complete the table by identifying and describing 2 types of software that can be installed on a computer to prevent threats over a network. Right, I think, well, let's say firewall. And I guess number 2, what we can say, antivirus or anti-malware. Yeah, I'm going to say both of them because, well, sometimes they call it antivirus, right? Sometimes they call it anti-malware. Right, so firewall description, I guess, well, let's say checks. Right, checks incoming, right, and outgoing packets. Right, and can deny or accept them. Right, yeah, can, all right, deny or, right, or accept them. Let's say, right, based on, right, a set of criteria. And I guess what, yeah, I know, like e.g. Right, detect. I know. All right, let's say what e.g. right, blocking like known malicious IPs. Right, let's say yeah, blocking known malicious IP addresses. Yeah, or I guess maybe like kind of like unwanted protocols. Yeah, I think yeah, like honestly, unwanted is probably not the best word, right? But I mean, when I say unwanted protocols, like let's imagine we've got a web server. Well, maybe we only want people to contact us, you know, with let's say HTTPS traffic, right? If someone is trying to send an FTP request, right, file transfer protocol, well, we probably don't want this because, like, why are they trying to, you know, transfer files to the server? Or yeah, why are they trying to download files from the server? And of course, you know, something like FTP, well, this does require a username or password, right? It's not just a complete free-for-all. Right then, antivirus or anti-malware, I guess we can say what are files? Yeah, okay, all right, let's say files will be scanned when downloaded, right? Since it's talking about over a network, right? So obviously sending, receiving files. Right, files will be right, scanned right, when downloaded. Right, and compared to a database. Right, compared to a database, right, of known malware. I mean, also you could mention, let's say, I know, yeah, behavior, or I guess, yeah, heuristics measured. Or I guess, or let's say behavioral heuristics measured. So I mean, when we say, you know, heuristics or well, behavioral heuristics, this is, well, obviously it's talking about the behavior, like what's the program doing. So if the program is, you know, let's say like, I don't know, maybe it's opening like thousands of files per second, right? It's modifying the file contents and then it's, you know, saving the files again. Well, that could be an example of ransomware, right? So it's obviously opening the files, encrypting the files, and saving the files. If you have some if you have some, you know, executable that, for example, is maybe it's like sending like gigabytes and gigabytes of data, you know, to one particular IP address. Well, that could be an example of spyware where, you know, maybe they're trying to like download all your files and of course, you know, send them to their server, for example. So yeah, if there's any suspicious behavior, so how can we say this, right? A database of known, okay, well, right, database of known malware, right, slash behavioral heuristics. I guess what can be blocked, yeah, files will be scanned when downloaded and compared to a database of known malware, right, slash behavioral, let's say behavioral heuristics analyzed. Let's say, right, suspicious files, or I guess executables, right, can be, and let's say, well, I guess what, deleted or quarantined. And of course, well, deleted is, yeah, or permanently deleted. Obviously, quarantined is well, put into a quarantine area, and then if the user wants to get it back, of course, they can click restore. Yeah, obviously, if they just want to delete it permanently, of course, that, you know, they can obviously delete it permanently. Right then, I think, yeah, the last one, all right, and this has been super long. Right, a video stores data in binary form, draw one line, right, to its matching denary value. Right, the smallest 8-bit integer that can be represented in 8-bit 2's complement. So I'm not just going to do it because, well, maybe I'll make a mistake. But let's say the smallest 8-bit integer, well, that's going to be a 1, right? Then, of course, well, just 7 zeros. So this is going to be, what, minus 128. And of course, since it's 2's complement, well, that's, you know, positive and negative. Right, the largest integer that can be represented in 8-bit 2's complement. So that's going to be, what, a 0 and then, well, 7 ones. So that's going to be, what, 127. Right, the largest unsigned, right, so, well, unsigned, right, only positive, right, integer that can be represented in 8 bits, so, right, that's going to be 255. And again, people should remember the formulas for this, right, so this one is going to be, what, 2 to the power, right, yeah, see, even I've made a mistake, right, 2 to the power of n minus 1, right, the largest here, so this is going to be, what, 2 to the power of n minus 1 minus 1, and yeah, I guess you can put that in brackets if you want. Right, then this is going to be, let's go minus, right, it's 2 to the power of n minus 1. Yeah, so try to remember these formulas. Right, the computer has a control unit, system clock, and control bus. Explain how the CU, right, control unit, system clock, and control bus operate to transfer data between the components of the computer system. Right, so I guess the control unit obviously contains the system clock. Right, yeah, okay, let's say that, right, the control unit, right, contains the system clock. Okay, Y, right, system clock, right, which, I guess, yeah, I guess what which generates timing signals. Right, let's say generates timing signals, right, to synchronize. Right, synchronize, I guess, yeah, the components, what, in the computer, or yeah, within the CPU. Yeah, okay, right, the components within the computer. Right, let's say, yeah, these, these timing signals are sent on the control bus. Right, these timing signals are sent on the control bus. Yeah, well, obviously, yeah, to ensure everything remains in sync. Yeah, I mean, I think we've said that really, but I don't know. Let's say it again just to sort of drive home the point. To ensure, right, all components, yeah, I guess remain, right, in sync. Yeah, obviously, hence can communicate effectively. Right, I think also, like, if we're talking about transferring data, I mean, they don't really mention it, but maybe the MAR, MDR. So yeah, let's say also, yeah, right, okay, well, so let's say, right, read and write signals are sent on the control bus. Read and write signals, yeah, are sent on, I guess what's sent, let's say from the CU on the control bus. Right, from the CU, let's say along the control bus. Right, and let's say, right, and the corresponding what, address slash data. Right, the corresponding, yeah, let's say address. Right, let's say, and like here I'm going to put data in brackets because, well, the thing is, obviously, I mean, when you're reading, okay, you only need an address, right? When you're writing, well, you're going to need an address and data. Because of course, well, I mean, yeah, obviously, well, you're going to need the data that you're actually, saving to memory. Right, let's say the corresponding, yeah, I've said corresponding twice again. Right, the corresponding address data, right, let's say from the MAR, MDR. Right, is, I guess, well, yeah, are sent, right, along right, that's going to be what, address bus. Let's say, right, address slash data bus. Right, let's say what, to be, yeah, read from, written to. Right, let's say, yeah, read from, right, slash written to. Right, the correct component. Since, I mean, obviously here it's talking about data transfer. So I think, talking about like writing data, reading data, that's going to be, yeah, part of data transfer. Yeah, I guess, well, let's say to the correct component. Right then, yeah, the last one. So complete the table by writing the register transfer notation for each stage of the fetch execute cycle in the given table. Right, program counter PC is incremented, so that's going to be PC. Right, and then we're just copying. So what we're copying the contents of the PC. Right, of course, that's what the brackets mean. Yeah, then just +1. Right, the data in the address stored in the memory address register MAR is copied to the memory data register or MDR. Right, this is the one with the double brackets. So of course we say, well, this is assigned to or copied to the MDR, and then, yeah, which is the double brackets. So of course, what the single brackets mean, contents of. Right, then if we have the double brackets, well, that's like saying, okay, well, let's say the MAR has the value 5. So if we say, well, here, right, the contents of 5, and then, well, the contents of that address. Now let's say let's say 5 has, the address 8. So we can kind of think of like removing the brackets, kind of pair by pair. So if we say, well, the contents of address 5 is therefore going to be 8, right? And of course, well, there we say, right, the contents of address 8, I don't know, maybe that's, 10, for example. So of course, right, in that value, in that situation, right, 10 is then copied into the MDR. Alright, anyway, guys, yeah, I think that's the end. Yeah, so I think that's been a super long video, maybe the longest one yet. But I mean, hopefully it's useful, and as always, any questions you can ask in the comments. And yeah, hopefully see you again in the next video.